Welcome to the fifth module of the Introduction to Python for BME series. In this module, we'll be covering image processing. Let's open up the Jupyter Notebook now. In this module, the task that we'll be trying to achieve is to differentiate between 1,000 handwritten images of zeros and 1,000 handwritten images of ones. And before you think that this task is unrelated to biomedical engineering, let's take a look at this picture of bacterial shapes. You'll notice that the coccus or spherical bacteria look kind of like zeros, and the bacillus or rod-shaped bacteria look kind of like ones. And the idea is that if we're able to differentiate between zeros and ones, then theoretically we'll also be able to differentiate between an image of coccus and bacillus bacteria that might be useful for a diagnostic test. The first thing we'll need to do is to load our 1,000 images of zeros and 1,000 images of ones. Our data set is contained in these two text files. And in each of these text files, there's going to be 1,000 images that are 28 pixels by 28 pixels. Each pixel will have two possible values, either a 0, which denotes a white pixel, or a 1, which denotes a black pixel. In this module, we'll also be using two different libraries. The first library we're going to be using is matplotlib, which is a really powerful Python plotting library that will allow us to visualize these handwritten zeros and ones that we're going to be analyzing. Additionally, we're going to be using another module called NumPy, which allows us to work with arrays and matrices more easily. So in the first section of our code, all we're doing in these 4 lines that I've just highlighted is to import the different libraries and set up the different settings that we're going to need for this module. In these next 2 lines, I've denoted the 2 text file names that contain all of our data. And in the last 2 lines in this cell, what we've done is imported the data, which is zeros or ones, which denote the pixel colors, into this variable called zeros. And one thing you'll note is this last bit of code here that says reshape. What this code does is that it converts all the zeros and ones that are in these text files into 1,000, which is this first parameter, images of 28 rows by 28 columns of pixels. And so now what we have in this variable zeros and in this variable ones is a 1,000 by 28 by 28 matrix of handwritten zeros and handwritten ones. Now that we've imported the data, what we want to do next is to visualize a sample of these zeros and ones so that we know exactly what kind of data we're dealing with, and we'll be able to see what it looks like instead of just knowing that they're in the variables. In order to do this, we need to plot a couple of the handwritten zeros and a couple of the handwritten ones so that we can get a good idea of what they look like. So that's what this following code does. The first line here is to say how many images we want to sample. In this case, I've defaulted it to be 10. The following line is just a for loop that basically plots using this command. So plt is our plotting framework, which we've imported up here. So it's saying plot using a subplot. So subplot allows you to plot multiple things in the same plot. Plot using a subplot the image zeros at I, the ith image of 0. So remember that in the for loop, we're iterating from 0 to 10. So remember that Python is 0 indexed. So the 0th image is actually the first image in zeros. And so we're going to plot the ith image of zeros, and these colons just mean that we want all 28 rows and all 28 columns of each image. So for I in range 10, we're going to plot each 0 and each 1. So in this case, we're going to plot the first 10 zeros and the first 10 ones. And so if you just type Control Enter and run the code, it's going to plot in one image. So that's why we did subplot, so that it could show all of these zeros and ones next to each other. It's going to show 10 zeros and 10 ones. And notice how all these zeros and all these ones are slightly different from each other, but you can still tell that they're zeros and ones. And just to review what we did, we wanted to plot a sample of 10 zeros and 10 ones, and we did it using a for loop because if we didn't have a for loop, we would have to write the code for each one of these individual subplots individually. So we used a for loop, and we called subplot to create the subplot. And what this command imshow does is that it shows the image. So it's kind of intuitive what it means. And the image that we're trying to show is the ith image in zeros and the ith image in ones. And to show the entire image, we want colon, which represents all the rows, and column, which represents all the columns of the pixels. And so now we have 10 zeros and 10 ones, and you can kind of get a general idea that all the rest of the 990 zeros and 990 ones look approximately the same. So now that we know generally what a couple of these zeros and ones look like, let's move on to analyzing the entire data set. So the first thing that we want to do is see maybe on average what all 1,000 of the zeros together look like and what all 1,000 of the ones together look like. And so far we've been dealing with just the binary image. So each pixel value can only be 0, which is white, or 1, which is black. So an idea to get what the average 0 or the average 1 looks like is if we just stacked all 1,000 zeros or all 1,000 ones on top of each other and looked at which areas in the image had the most popular pixels. And that's known as something called a heat map, and you may have heard of that before. What a heat map shows is basically which pixels were most frequently written when someone wrote a 0 or someone wrote a 1. And so if you wanted to just stack the 1,000 images on top of each other, the best way to do this is to use a NumPy function called sum. Basically what this does is it takes all 1,000 zeros in this line and it sums them on top of each other. And what this axis means is that you want to sum 1,000 images, the first dimension, as opposed to summing the 28 rows or the 28 columns on top of each other. So the 0th axis is the first dimension, which if we remember from up here, the first dimension represents which of the 1,000 images we're looking at. So going back to here, what we're doing is that we're going to sum all the zeros and we're going to sum all the ones, and then we're going to show what that summed or average image looks like in a heat map. And now when we sum all the images on top of each other, each pixel is no longer binary. For example, you might have a pixel with a value of 500 or another pixel with a value of 900. And now the value of each pixel represents how frequently someone wrote over that pixel when they were writing a 0 or a 1. So let's press Control-Enter to run this code. Cool, now you'll see that here's the average image of what all 1,000 zeros look like when they're stacked on top of each other. And here's the average image of all 1,000 ones, what that looks like when they're stacked on top of each other. And you'll see here that for the zeros, the average 0 looks like what we'd expect. And it seems to be the case that these super dark red regions at the top and bottom were most frequently written on. And for the ones, these dark red pixels here in the middle were most frequently written on. Now that we know what the average of the 1,000 zeros and the average of the 1,000 ones looks like, let's try to look for some features between them that we can use to discriminate between whether an image is a 0 or a 1. So over here I've listed 5 of the different features that I've noticed, and let's point them out now. So the first thing to notice is that the 0 on average has way more pixels in it than the 1. And that's pretty easy to figure out why, because the 0 is essentially a circle, and a circle is, the circumference of a circle is pi times the diameter, which is around here. So compared to a 1, which is just a straight line, this straight line is kind of like the diameter of this circle. And so on average, I would expect the 0 to be around pi times the height of this 1. And so basically the first discriminating feature is really simple. The sum of the total black pixels in any given 0 image is going to be much more than the sum of the total pixels in black pixels in an image of a 1. And that's just because 0 is like a circle and 1 is like a line, and there's way more pixels in a circle. The second discriminating feature is that in this image of a 0, the middle of the image right here around pixel 15, row 15, column 15, the middle of the image is relatively unoccupied because the 0 is like a circle, and again, the middle of a circle is empty. However, in the 1, on average, people write the 1 passing through the middle of the image. So we see that pixel 15 here has a lot of pixels that are dark. And so the second feature is that in this 28 by 28 image, the middle is mostly empty for zeros, and it's mostly filled for ones. Another discriminating feature is that, again, because the 0 is circular, in the middle of the 0, the middle of the image, around row 15, the 0 is much fatter or wider than the middle of the image of the 1, as you can see here. So over here, row 15, the 0 is much wider than over here in the 1. The fourth discriminating feature is that in the 0, there's something called 90-degree rotational symmetry. What that means is that if I take this 0 and I rotate the image by 90 degrees, it still looks mostly like a 0, and that's because, again, a 0 is a circle, and if you rotate a circle, you still have a circle. Whereas if I rotate this 1, which is like a vertical line, by 90 degrees, it becomes horizontal, and it no longer looks like a 1. And we're going to see how we can exploit that later on. And finally, the last feature that I noticed was that in this corner of the image right here, in between rows 15 to 20 and columns 20 to the rest of the image, so in this particular corner right here, there's a lot of pixels in the 0. But if we look at that same region for the average image of the ones, there's almost entirely no pixels. And this is kind of the reverse of looking at the middle of the image. So in the middle of the image, the 0 has almost no pixels and the 1 has a lot of pixels. And so I just wanted to find another feature, which was this area of the image that had a lot of pixels for the 0s and almost no pixels for the 1s. So now we're going to look at each one of these discriminating features individually and see which one allows us to best discriminate between the 0s and the 1s. So the first thing that we wanted to look at was the total number of black pixels in each individual image, because our idea was that for the 0s there would be a larger total number of black pixels than for the 1s, because 0s are a circle and 1s are kind of like a diameter. And so what we need to do is we're going to need to sum up all the black pixels, because remember, those have a pixel value of 1, whereas all the white pixels have a pixel value of 0. So we're going to need to sum up all the black pixels per image for each of the 0s and each of the 1s. And then if we plot a histogram of how many pixels were black for the 0s and how many pixels were black for the 1s, then maybe we can compare them and then get a good idea of how well the total number of black pixels allows us to distinguish between the 0s and 1s. So the way we do that is, let's keep a list of all the total number of black pixels for the 0s here, and a list of all the total number of pixels that were black for the 1s here. And now we have a for loop that iterates through all 1,000 of each of the 0s and 1s. And then what we do is we simply sum the ith image of 0s. And the reason we do that, again, is because the black pixels have value of 1 and all the white pixels have value of 0. So if we just sum all the rows and all the columns in the image, we'll get the total number of black pixels. So here we're summing the ith image of 0s, and here we're summing the ith image of 1s. And then what we're going to do is append that total sum to the 0s black list and the 1s black list, and we do it for all 1,000 images. And after we've done that, what we can do is use matplotlib and plot a histogram. And the way this histogram works is that it's going to plot all the total number of black pixels for the 0s and all the total number of black pixels for the 1s. And it's going to plot them on the same plot so that we can compare them. So let's do that now. Press Control-Enter to run this cell. And cool, this is what we get. You see that we get what we anticipated actually. We thought that there would be way more black pixels for the zeros because the zeros look like a circle. And the zeros, which are shown in light blue, do have a much higher number of total black pixels, as you can see down here. Whereas the ones are shifted, the histograms shifted much further to the left, implying that there's way fewer number of total black pixels in each image. And that's kind of what we expected. And so on our first try of just looking at the total number of black pixels, we already get a pretty good idea that this might be a good discriminating feature between the zeros and ones. And it turns out that we didn't actually need to write this for loop and append each one of these total black pixel sums to the list, because Python, remember, has list comprehensions. Another way we could have written it is in a single line like this. So what this is saying is that I want to put into zeros black a list of the sum of each individual image I in the zeros for I in range 1000. And basically, this list comprehension here is exactly the same as what we've done in the for loop, but in a much simplified form. Similarly, for the ones black, what we're doing is I want to put the sum of all the black pixels in the ith image in ones for I in range 1000. And basically, if I run this code, we should get the exact same histogram as the one that we got right here. So let's do that now. And you see that you get the exact same histogram. And basically, the whole point of doing that was just to show you that list comprehensions are really powerful in Python. And going forward in the rest of this module, we're going to be using list comprehensions in order to analyze data. So the next feature that we wanted to look at was the total number of black pixels in the center of the image. And if we look at the average zeros and the average ones again, it seems like the pixels in the center around row 12 through row 16 and column 12 through column 16 seem pretty empty, whereas that same region in the ones look pretty filled. So what we're going to do is basically do the exact same thing that we did with the total number of black pixels, but now instead of summing all of the rows and all of the columns, we're summing the 12th through the 15th row. And remember that when we do index slicing, it excludes the second index position. So it's actually 12 through 15, not 12 through 16. And the 12th through the 15th columns for zeros, which is the middle of the image. And we're taking the sum of all the black pixels in that same region for the ones. And we're going to plot a histogram again to see what that looks like. And our hypothesis, remember, was that in the middle of the image there would be much fewer black pixels for the zeros than for the ones. So let's plot that now by pressing Control Enter. And cool, we got exactly what we expected. For the zeros, in the middle of the image, there's very few black pixels. And for the ones, shown in the light orange, there's many more black pixels. One thing to note here, though, is that there's quite a bit of overlap in the middle regions between 6 to 14 pixels, where a lot of the images of the zeros and a lot of the images of the ones overlap with each other. And so maybe this feature of the black pixel in the center isn't as good as just taking the sum of the total number of black pixels, which has much fewer overlap. The reason overlap is bad is because in this region, because there are some images with zeros, some of these images are zeros and some of these images are ones, it'll be really hard to tell exactly which is which. And so you want to minimize this overlap in order to get a feature that's really discriminatory. And so yeah, that's maybe why we'll have to consider a couple of the other features. So the next feature that we want to look at is the width of the middle of the zeros and the ones. And remember we said that in the average image, around the 15th row, the width is much wider for the zeros than for the ones. And so to calculate the width of the image at row 15, what we're going to have to do is look at this row, and we're going to have to look at the difference between the first index position or the first column that is black and the last column that's black. And the number of pixels in between those, or the number of index positions in between those, will be the width. And this is going to be a little more complex than just taking the sum of the total number of images. So let's write a function to calculate the width of the image. The way we're going to do that is that if we have an image, in this case, it's going to be just a single row. So we're not actually taking the whole image, we're just taking a single row of the image. What this code does is that we first calculate the maximum or the last index position for which that row is non-zero. Because remember, if it's non-zero, it's black, and np.max gives us the maximum. So we're getting the maximum index position that that row contains a black pixel. So that should basically be the rightmost pixel position that is black. And then to calculate the width, we just want to subtract the minimum index position of a black pixel, which is the leftmost part of the image of that row that's black, and the difference between them will be the width of the image. And here it says 13, but remember we want the 15th row, and remember Python is 0 indexed, so the 15th row is actually the 14th index position. And basically what this code is saying is we want to get the width. So width is this function that we just wrote. It's going to calculate the width at the 15th row for all 1,000 zeros, and it's going to put them in this list. And it's going to calculate the width for all the ones, for all 1,000 ones, and put them in this list. And then we're just going to plot the histogram again and see what the histogram looks like. So Control Enter to run this cell. And cool, this feature seemed to work out really well. So the zeros are shifted all the way to the right, and the ones are shifted all the way to the left. And so that's exactly what we wanted, because we thought that the width of the zeros in the middle would be really wide and the width of the ones in the middle would be much narrower. And there's very little overlap here. There's actually less overlap than even taking, or actually around the same overlap as when we take the total number of black pixels. So it seems that from what we've done so far, looking at the width of the middle of the image is a really good feature that discriminates between zeros and ones. The next feature that we wanted to look at was the total number of black pixels in this middle bottom right area of the image, because we saw that it was pretty filled for the zeros and it's pretty empty for the ones. And so the way we want to do that is that this region looks to be around the 15th row to around the 20th something row, and the 20th something column all the way till the end of the image. And so basically we're just going to slice that part of the image and take the sum. So this is kind of similar to what we've done before. So in the middle right, we want the 15th row, which is around the 14th, which is actually the 14th index position because Python is 0 indexed. And we want it up to, say, the 20th row. And remember, because it excludes the second index value, this is actually 21. And then this 20 colon just says we want the 20th column all the way to the right. And so this will compare the bottom right of the image. And basically we're doing what we've done before, which is we're taking that region of the image, we're taking the sum of it, and we're taking the sum of it for all 1,000 images. And then we're storing that in a list. And then we're going to plot the histograms and compare. So let's do that. Control Enter. Cool, what we'll see is that for the ones, there's almost no black pixels in that region of interest. And for the zeros, there's anywhere from 0 to 34 black pixels in that region of interest. And so it seems that the black pixels in that particular region, the bottom middle right of the image, is actually a pretty good indicator of whether an image is a 0 or a 1. It actually, almost 980 or so of the ones have 0 black pixels in that part of the image. And so if you're just trying to figure out if an image is a 1, then 98% of the time it won't have a black pixel in that bottom area of the image. So this seems to be a really good discriminating feature as well. So the last feature that we wanted to test was rotational symmetry. And if you'll remember, rotational symmetry was the idea that in this zero, if we rotated it by 90 degrees, it would still look like a zero, but if we rotated the 1 by 90 degrees, it would look like a horizontal line instead of a vertical one. And the idea that I wanted to test was that if you rotate the 0 and you overlay it on top of the original 0, it's going to look almost exactly the same. But if you rotate the 1 and you overlay it on top, only these middle pixels will be the same, because the 1 will lie horizontally across and only the middle pixels will look the same. And so what we're going to do is we're going to first plot this cell. So let's plot it first, and then I'll explain what's going on. So Control Enter to plot. So what we see here is an individual image of a 0. That's this line. So we're just plotting the first 0. In this next cell, what we're doing is we're rotating the 0 counterclockwise by 90 degrees. So we took this 0 and we just rotated it counterclockwise. And then what I thought was, if 0 has rotational symmetry, if I stacked these two images on top of each other and I looked at which pixels they shared, there would be many more for the 0s because of the rotational symmetry than the 1s. Because if I rotate the 1 and I stack it on top of each other, only the middle pixels will be shared. So in order to calculate the middle pixels that are shared, what you can simply do is take the original image of the 0s here and multiply it by the rotated image. And the key thing to note here is that in NumPy, this multiplication sign isn't matrix multiplication. Instead, what it is called element-wise multiplication. So basically it takes each pixel position in the first image and multiplies it by the same pixel position in the second image. Therefore, any pixel that's white in either one of the images, that same pixel will be white in the overlaid, multiplied image. And that's the same thing as saying, take this image, stack them on top of each other, and look at which pixels are black. So what we're going to do now is we're going to basically take the sum of the stacked images, and we'd expect that for the 0s, because of the 90-degree rotational symmetry, there's many more black pixels. So what we're going to do is here, using list comprehensions again, we're going to take all of the 0s, multiply them or overlay them with the 90-degree rotated 0s, and then we're going to take the sum of the black pixels for all 1,000 zeros. And we're going to do the same with the 1s and plot the histogram again. So Control Enter to run. And we see that it's maybe not as good as some of the results we had with some of the other features, but we can still see that for the 0s, it's mostly shifted to the right, and for the 1s, it's mostly shifted to the left. However, if we had to pick one best feature to discriminate between the 0s and the 1s, it would probably have to be either the width of the image, the width of the handwritten 0 or handwritten 1, or the feature that we tested at the very beginning, which was the most simple one also, which was just to take the sum of the total black pixels in the image. And so now we've seen all 5 different features. So we've seen the total number of black pixels, we've seen the number of black pixels in the middle of the image, the number or the width of the handwritten 0 or 1, the total number of black pixels in the middle right of the image, as well as the rotational symmetry of the image. And your task now, or your assignment, is to do the same kind of analysis except with a twist. Instead of just looking at the 0s and the 1s, you're going to be looking at the 0s, 1s, and a data set of 1,000 images of handwritten 2s. And so the code to load that is here, and I'll leave it up to you to find a single discriminating feature, which could be maybe one of the 5 that I've shown you guys how to do here already, or maybe a new one that you want to discover on your own that will allow you to discriminate between 0s, 1s, and 2s. Good luck and have fun.